Hi everybody. Okay, so here we are moving on next unit in chemistry. So unit 10 was gases, unit 11 is going to be solids and liquids, and we will cover some of just the characteristics of those two states of matter. Good news, bad news, there's not math in this unit. It is strictly concepts, theories, and it's a fairly short little unit. And several of the ones that follow afterwards will kind of touch back on these because of the characteristics of solids and liquids, and we'll put them together for solutions and different things. And so I think I told you this before, but if I haven't, in at least the way our class has been formatted so far, we've really covered big topics in chemistry, the mole or equations or stoichiometry, whatever it is. We're moving into some of the more specialized topics and units, and so that's kind of where we are at now. So if this seems too simple for you, you're welcome. Okay, so here we go. So first off, we're dealing with states of matter, and there are two characteristics, conditions, tendencies that determine state of matter, again, that and we've already talked about this, but the first one is kinetic energy. And so remember, all states of matter have particles that are in constant motion, from solid, just the tiny vibrations in place, to the flow of a liquid, to the all over the place of a gas. And so that level of energy helps determine the state of matter, and also the forces of attraction. And so how strongly are they held together? It's related to bonding, again, which we talked about last semester. We will kind of retouch on some of that again. But these two characteristics, kinetic energy and forces of attraction, are kind of the push-pull on, if things stay together or apart, and how those balance out will tell us if we're dealing with a solid, liquid, or a gas. Okay, so with these forces of attraction, we're going to talk about them in terms of intermolecular attraction, so holding the entire substance together, not just a compound. Sometimes these are called van der Waals forces, just so you know. But recall that, because we're going to talk about polar, nonpolar molecules, a polar molecule has an asymmetrical shape from the Vesper chart, and then also the electronegativity value difference is between 0.5 and 1.6. We'll talk about easier ways than that, to just quick easy ways to determine polar, nonpolar. But as far as intermolecular stuff goes, in polar molecules, we have first off what is called a dipole-dipole attraction, and this is attraction between polar molecules, and it is based on a positive and a negative attraction. Remember, just like magnets, positive negatives will stick together. That's kind of the most common, kind of the general, this is what is holding them together. In some very specific polar molecules, we see hydrogen bonding. And this is a very strong type of dipole-dipole bond, so it's still between the positive of one molecule, the negative of another, and it occurs, like I said, specifically between hydrogen in one of the molecules and either N, O, or F in the other molecule. Sometimes I will refer to these as the NOF bonds. I don't know where I learned that, but that's stuck in my head. And so if you see hydrogen with oxygen, like you do in water, or hydrogen with fluorine, or those, and that is a dipole bond, but a very strong type of dipole bond. It's the strongest bond type, or strongest type, not bond type, but strongest type of intermolecular attraction between that two molecules can have. Okay, so we've got dipole-dipole hydrogen bonding. And then for nonpolar molecules, we have what is called London dispersion forces. And these are fairly weak forces of attraction between nonpolar molecules. The strength of the attraction has to do with the size and the mass of the molecules themselves. The higher the mass, the higher the attractive forces. And so then my little question there, is this a direct or inverse relationship? Well, if the mass goes up, the force goes up, so that is a direct relationship. And the way it works is that, remember, these molecules are constant motion, kinetic energy, making them move. When they bump into each other, when they strike each other, it is possible just for a split second that the electrons can be displaced, and the molecule will look or become dipole just for that instant. And in that instant, the two molecules would be attracted to each other by the positive negative of like the magnets, just the same as the dipole bonds. And so is happening so fast and so repetitively, and so instantaneously, and all these things that stuff is not falling apart and then coming back together, falling apart. It stays together because all of that rearranging is happening so quickly. And again, back to the, it's stronger when their mass is higher. The higher the mass, the greater the number of electrons to be displaced, which means the greater the attraction is when they are rearranged. On like our test that we'll take over this, I'll ask you what type of intermolecular force is holding stuff together. And the main thing is to know whether we're dealing with polar or nonpolar molecules, and then whether it's an H with NO or F interaction there. Okay, so now states of matter. We talked about this already a little bit. So on my little picture there with the comparison of the forces of attraction, that's Fa, and Ke is kinetic energy. Gases have much more kinetic energy than they do force of attraction, and so that's why they spread out. Liquids have approximately the same. The force of attraction are approximately equal to the kinetic energy. That's why there's the flow that we don't see, but that we know is going on, but also the attraction that is keeping them together. And then with solids, the force of attraction outweighs the kinetic energy, so you see them staying together. And in order to change from one state of matter to another, we can change the kinetic energy by adding heat or by removing heat. And so that's why when you boil water, you're giving it more kinetic energy through that heat. It eventually will start to boil and become a gas. Same thing if I take water and stick it into the freezer, I am removing kinetic energy. It is losing the motion, and so as the molecules stop moving so much and settle into place, you go from a liquid to a solid. And so that's one way to determine it, and this is called a phase change. And when the temperature change happens, that's when you see these phase changes happening. Okay, so these are the kind of the three big phase changes that we'll deal with. They occur at the boiling point, which is also the condensation point if you're going the opposite direction, the freezing point, which is also the melting point, and then sublimation is kind of an unusual one. We're not, this is not something is common to all substances, but that is a solid to a gas. And deposition, very often, it kind of depends on the text, is the term for the opposite, gas going back into a solid. So the diagram that's going to be on the next page is called a phase diagram, and it shows all three states of matter for one substance based on pressure and temperature. And there are 2 points that I want you to be aware of. There's the triple point, and this is the temperature and pressure at which all three states of matter coexist. Typically, that is only under lab conditions. It's not often that you see all three states of matter in one place at one time. And then you have the critical point, and this is the point at which, no matter how much pressure you apply, you cannot force the gas back into liquid form. And you can't force the molecules to stick together, to get close enough to become liquid. Okay, so here is the graph. So this is a phase diagram. So, excuse me, you've got solid over here, and then liquid is this section, and then the gas is down here. Pressure, you can see, is increasing as you go up, and then temperature increases as you go this way. And they are, you don't have necessarily ranges on here, but it's kind of just a general diagram. And then it gives you the changes, melting, freezing, vaporization, condensation, sublimation, deposition, all that stuff. What I want you to note, the triple point right here in the middle, right where all 3 points meet. So there's the triple point. And so you, at that pressure, whatever it may be, and at that temperature, you have all 3 states of matter. Again, this is typically under lab conditions, under very controlled conditions. And then up here you have the critical point. And so this one is, so no matter what I do, I cannot apply enough pressure to get that substance to go from gas back to a liquid. Again, every substance will be different as far as their phase diagram looks, but it's kind of the general picture. Okay, so phase changes. This tip, I just wanted you to know, make sure you know what's happening. Freezing is when you go from liquid to a solid, melting, solid to liquid. So make sure that you know those, what states of matter you're dealing with on those. I'm not going to write them down just for time. Okay, then our next graph, this is very often called a warming curve. Sometimes they'll call it a phase change diagram, but what you see on these graphs is as you increase the temperature, so here's temperature over here going up, over time, which is the x-axis there, you will see the phase change, the temperature will level out during that time. So if we're talking about water, for instance, this temperature is 0 degrees. That's where water freezes, but also where it melts if you're going back. Then this temperature is 100 degrees. And so that's where it would boil. Excuse me, my nose is itchy today. Okay, but on this phase, or on this diagram, excuse me, anything below 0, if we're talking about water, is a solid. And then when you get to 0, the solid will start to melt and you'll go from a solid to a liquid. At that temperature, you will see the phase change start to occur, and until all of the solid has become a liquid, it will maintain right at 0 degrees. This is because the energy that is being put in to raise the temperature now is being put into breaking the bonds between the molecules. And so the temperature levels off, energy is still going in, but it's breaking bonds. So then the next phase, between 0 and 100, water is a liquid. At 100, you see another phase change where you go from liquid to a gas, and that is, again, a level spot because now temperature's not going up right now. That energy is being put into breaking the bonds. Notice that this is a longer time span because it takes way more energy to go from a liquid to a gas than from a solid to a liquid, and of course up here is a gas. We will use this graph much more with some math in units to come, so you'll see it again. Okay, now 2 liquids. We've got 2 main characteristics. First off, liquids have the ability to evaporate, and this is where and evaporation is very specific. It's the conversion of a liquid to a gas at the surface of the liquid, and the liquid is not boiling. And so what happens is the high energy molecules at the surface leave the liquid, escape as in the gas form when they gain enough energy. They gain this energy from collisions with each other. And so remember, they're in there flowing, and as they continually run into each other, momentum is built up in one of the particles that is in that collision. And once it gains enough momentum, it will leave the liquid as a gas. That is evaporation. Typically, evaporation is called a cooling process because as the high energy molecules leave, they're taking energy with them. Remember, we can sense kinetic energy as heat, as temperature, so they're taking heat away and the temperature becomes lower. This is one of the reasons you feel cool when you or you feel cold maybe when you get out of the shower. Your skin is still kind of damp, even if you're dried off. There's still some dampness to your skin. That's water, and as it is still warm and your skin is actually warm, it gains enough energy and leaves, and it takes some of your heat with it, and that's why we sweat. It helps to cool you off, and so that's what you're feeling there. Okay, a couple things related to evaporation. Volatile liquids are things like rubbing alcohol is a good example. They are liquids that evaporate very easily at room temperature. Viscosity is typically defined as liquids that resist flowing, like thick liquids. And in terms of evaporation, thick liquids do not evaporate easily. Okay, second characteristic, vapor pressure. Liquids have vapor pressure, and this is pressure that is produced as a liquid evaporates. And so I have two fantastic little visuals here for you. Two containers, equal amounts of liquid A and liquid B. After a while of just sitting there, you have containers that look like this. Those little dots are my fancy way of drawing like gas molecules. I'm representing evaporation. Okay, so thinking back to what we talked about with nonpolar molecules versus polar molecules, typically polar molecules are going to stay together better. Water is a polar molecule. It evaporates, obviously, but it takes a lot for water to evaporate. So anyway, so A or B, which contains nonpolar molecules, that's going to be B because it evaporates or has evaporated more, and then the polar molecules would be A. Which liquid has the higher evaporation rate? Which one has more specks in it, more gas molecules? B. Which goes along with B also being more volatile. Which has the higher attractive forces? Which one is held together better? A, that's why it hasn't evaporated as much. And then which has the higher vapor pressure? The vapor pressure is all the dots, so that one would be B. Okay, so now another fantastic visual. If you heat the liquid, so say we have a liquid and we heat it up with our fancy little Bunsen burner, what happens to the number of molecules in the vapor phase, so the specks? That the number would go up, so it would increase because you're again giving it kinetic energy. And then does vapor pressure increase or decrease when you heat the liquid? Big old increase. Okay, now another graph, we've got vapor pressure curves. Vapor pressure curves typically show you the normal boiling point, and it is the temperature at which the vapor pressure of a liquid, so the pressure above the surface of the liquid, equals 1 atmosphere. And then I asked this question, what is the relationship between temperature and vapor pressure? Looking at that graph, notice that is temperature goes up, vapor pressure goes up, so that is definitely a direct relationship. But also notice, so the little dots on there, those are just the different points as this temperature increases, and then it gives you the little, so here is a 1 atm at 100 degrees Celsius, that is the normal boiling point. This is a vapor pressure curve for water, obviously. And so depending on what the substance is, you would have different boiling points based on where that curve is or where it hits at 1 atm. You could use this for any of the pressure standards. You know, we could have 101.3 kPa or 29.9 inches mercury, whatever it is. Typically, though, you're going to see it with in terms of atmospheres. Okay, so now here's a graph question for you. This is something like you might see on the ACT, by the way. It wants to know which liquid has the highest boiling point. So again, based on what we just talked about, and this one actually is in millimeters mercury. Remember that is 760. So the little dash dotted line going across there, that's the normal boiling point. Oh, it labeled it 1 atm for us. The highest boiling point is this dark green line that's all the way out here. Looks like it's about 350. And so that dark green is that liquid. I don't know what they are, obviously. And then which one has the lowest attractive forces? Which one's going to boil the fastest or at the lowest temperature? Looks like that one is the purple line. So again, it's just kind of reading the graph. Okay, then a little question for you. So the atmospheric pressure in Denver is less than the pressure in Bartlesville. Will water boil at a higher or a lower temperature in Denver? So typically, because there is less atmosphere above, well, there is, not typically, there always is less atmosphere in Denver, or pressure in Denver than there is in Bartlesville. Water will boil at a lower temperature because it's easier to build up that pressure with less pressure on top of the water. I know. Think about it. I did not say that very well, but think about it. And if you like read the instructions on like muffin mixes or cake mixes, a lot of times they'll say at higher altitudes bake differently, and that's why. But then the second question, if you want to hard boil an egg in Denver, will you have to cook it for longer or shorter than in Bartlesville? Now, here's the deal with that. You would actually have to cook it longer to hard boil it because it's going to boil at a lower temperature. And it's not significantly lower. You know, here in Bartlesville, it would boil at 100 degrees Celsius because we're pretty close to sea level. In Denver, it's going to boil at, like, let's say 95 degrees. And so when I hard boil an egg, I hard boil it for, after the water comes to a boil, 10 minutes, and it is hard boiled. In Denver, I might have to boil it something more like 12 minutes or 15 minutes or whatever it is. That's because it's going to boil at a lower temperature, so it hasn't actually officially gotten to the 100 degrees that I'm used to. Okay, so now moving on, solids real quick here. We're just going to run through some of the characteristics. So most solids are crystalline in nature, and that means that they have a very internal, orderly, repeating 3D pattern. Their individual crystals will have a very regular shape, with very distinctive edges to them. Like the picture that I have on your screen there is a highly magnified picture of salt crystals, and notice that they have 90-degree angles. They're very cubic. Some are more like hexagons, or whatever it is, very different geometric shapes. Crystalline solids have definite melting points. They will melt at 35 degrees, or whatever it is. They will cleave along a certain plane. That means break, and that goes back to the angles on the crystals there. And then some good examples, diamonds. That's one of the reasons that you can cut diamonds in certain ways to make them shine more, have different different facets, different faces showing. Ice. If you've ever bitten into like a big ice cube, if you look after you've bitten it off, it's very jagged, but it's very it's not random shapes. They're very uniform. Salt is the picture there. So most solids are crystalline. Some are amorphous. Amorphous is basically the opposite of crystalline. So they lack this ordered internal structure. They tend to start melting and then melt over a wide range of temperatures, so their phase diagram is kind of weird looking. And then when you break them, they break into irregular fragments with irregular angles. My picture there is just some glass that is shattered. And notice that, there are straight edges and there are corners on some, but not on others. And so very random. Rubber. If you froze rubber and then broke it, again, would shatter into pieces. Plastic, soot, which we don't really think of as solid, but it's, like you get it out of the fireplace kind of a thing. Okay, now, last but not least, just to wrap up attractive forces. When the attractive forces between molecules are high, so when it's held together very well, the evaporation rate would be low. It's still going to evaporate eventually, but just not as quickly. If evaporation rate is low, that means volatility is low and the vapor pressure is low because it hasn't evaporated. But on the other hand, that typically means the surface tension is high, and we'll cover surface tension. You guys will do some book stuff, and we'll do really exciting stuff and watch water boil and those kinds of things. But surface tension is high, viscosity is high, and the boiling point is also high. It takes a higher heat to boil it. And if I flipped this and said that when the attractive forces are low, everything would just reverse. Okay, so ran through that super quick. I'm sure some of it was kind of crazy. Um, a lot of this is common sense though, so just kind of think about it. Of course, we'll go over in class. Ask questions. Bye, guys.